Well, welcome and thank you for joining. Let's take a look at another homework question. This time we are on lesson U5L2, question 17. So we're given a parallelogram OPQR. So OPQR. And in this parallelogram, we know that one of the sides is represented by vector OP with coordinates negative 7, 24. The other side of the triangle, side OR, is represented by vector OR with coordinates negative 8, negative 1. We need to find the angle made between the vectors OR and OP, which means we're trying to find this angle theta here. Now, by lesson U5L2, you hadn't been introduced to dot and cross product. And the only way we could find angles when we were in 2D was by using the tan ratio, and in 3D by using direction cosines. So for example, if you are here on the Cartesian plane and you have two vectors in standard position or two position vectors with tails coming out of the origin, then to find the angle made between these two vectors, we would find the angle that each vector made with the x-axis. So we did that by using the tan ratio, y over x. So we would find the angle that vector A makes with the x-axis, and then the angle that vector B makes with the x-axis, and then we would reason about the location of the vectors to understand what the actual angle is between the two vectors, and then we'll have to add them and figure out what the angle between two vectors was. So we are going to follow the same strategy or a similar strategy in this case. So to find the angle made between vectors OP and OR, we will have to find the angle that OP makes with the x-axis and the angle that OR makes with the x-axis, and then try to figure out what this angle would look like and what the measurement would be. So we're going to start off by saying that we need to give a name to those angles that we're trying to find. So we're going to let theta 1 be the angle that vector OP makes with the x-axis, and theta 2 will be the angle that vector OR makes with the x-axis. Recall that coordinates of OP are negative 7, 24. Coordinates of OR are negative 8, negative 1. So to find the angle theta 1 then, we will have to use inverse tan 24 over negative 7. So use a calculator for it, and the calculator probably will give you the answer, negative 73.7 degrees. Let's try to draw this angle on the Cartesian plane and see what that looks like. So negative 73.7 would be the angle going clockwise from the positive x-axis. So this would be the angle the calculator gave us. Now remember, the calculator will give us the smallest possible angle the calculator knows with a given ratio. Now we have to think, what is the angle that our vector makes with the x-axis? Now, with coordinates negative 7, 24, it means that our vector must be somewhere here in quadrant 2, where x is negative and y positive. So our vector then must be located somewhere here then, in the second quadrant. And this would be vector OP. And I'm going to write this angle in here, negative 73.7, because we're going to have to use this. Now let's continue with finding angle theta 2. For theta 2, we're going to use the inverse tan of y, which is in this case negative 1, over x, which is negative 8. So if you use the calculator for it, then you get inverse tan. Negative 1 over negative 8 would be equal to the angle 7 degrees. So that's an interesting angle. So the angle that is 7 degrees will be this one here on the first quadrant. Okay, so I'm going to draw a tiny little angle here. Obviously, it's not very accurate. I'm exaggerating it a little for the purpose of being visible. So that would be the angle 7 degrees. Now, recall that the coordinates of OR are both negative. And where are the coordinates of points both negative? I would say they would be in quadrant 3. So that means that our actual vector is not in quadrant 1, so the angle is not 7 degrees, but something related to it. So vector OR will be here. So if you put the vectors together on the same diagram, so it means that the angles we have here, so if we place them together, actually I'll try something interesting, or I think it's interesting. So I'm going to bring this Cartesian plane here with the origin right at the same place here. Oh, that works out. So we're going to say that if this is vector OP, OP, yes, and this is OR, let me grab the leg of R here. So therefore, the angle made between these two vectors will be, so take a look at this. So it would be this angle here, which is made of this little angle, which is 73.7 degrees based on our calculations. And this little angle here, which is simply 7 degrees. So the angle made between the two vectors will be theta equal to, so remember this was our theta 1 right here, and this is our theta 2. So theta would be equal to 73.7 plus 7. So that will make it 80.3 degrees. So that's the angle made between OP and OR. Now, in a similar, another method, not in a similar way, but another method would be by using the dot product. But that happens after lesson U5L2 actually, so it happens in the coming lessons. But when you prepare for the unit test, you would know this theory. And using dot product means that you can dot product the vectors in algebraic form. You can find their magnitudes. Try that using dot product. I will actually treat this problem again from a different perspective. Okay, so in question 17b, we need to find the acute angle between the diagonals OQ and RP. So what I'm going to do actually is grab the same diagram because I don't want to make the diagrams too crowded. So, actually I prepared it before. Cool. So we're trying to find the angle made between the diagonals OQ and RP. Let me see if it is the exact. Okay, OQ and RP, perfect. Now the coordinates of OP are -7 and 24, so I'm going to write that down. So -7 and 24. And the coordinates for OR were given, I think, -8 and -1. Let me double check, yes. So -8 and -1. So if we want to find the angle made again between the diagonals OQ and RP, then we will have to again find the angles that OQ make with the x-axis. So we're going to let alpha 1 be the angle that OQ makes with the x-axis. Okay, so this is taking a little bit longer. So, but here I have a trick, and now you know all my tricks. So I will resize it, make it a little smaller. Let me copy this so we won't have to write similar things so many times. Wish we could do that on a test, huh? It would save a lot of time. Okay, and we're going to let alpha 2 be the angle for the vector RP this time. Okay. Now, just like we did in the previous example with finding the angles of two sides, we're going to try to find the angles that OQ makes with the x-axis and what RP makes with the x-axis. Now, remember how we did this? So we did this by finding the coordinates of each respective vector. So Sorry, I have to resize. This is too small. Okay. So first we need to find all the coordinates of OQ because we don't know it yet. Okay. So OQ is a diagonal, one of the diagonals of parallelogram, and based on the parallelogram, or let's put it this way, parallelogram law of addition, that would be the sum of vectors OP and OR. So we're going to write that down here. So OP plus OR would give OQ. So coordinates of OP are -7 and 24. Plus vector OR, which is -8, -1. To add two vectors, we simply add the x coordinates together, the y coordinates together. So we're going to add this -7 and -8. That will make the x coordinate. And for y coordinate, we have 24 plus -1. -7 plus -8 is -15. 24 plus -1 is 23. So with this, we obtain the coordinates of OQ. In a similar way, now we're finding the coordinates of RP. Now, vector RP would be equal to RO plus OP. Now, I know the coordinates of OP, but not exactly for RO. But isn't RO the opposite of OR? So we can write it as -OR plus OP. So that means we have negative for OR. We have -8, -1. So we're taking the opposite of it. And for OP, we have the good old -7, 24. There we go, right here. So let's simplify. We have 8 and 1 for -OR and -7 and 24. So together they will make 8 plus -7. That would be the x coordinate. And 1 plus 24 will be the y coordinate. So therefore, coordinates of RP are 1 and 25. So we got the coordinates of both OQ and RP. Now the process of finding the angle made between them is very similar to the process of finding the angle made between these two sides in the parallelogram. So we're going to have to find the angle alpha 1. Alpha 1 is inverse tan, 23 over -15. Use the calculator. So second tan, 23 over -15. My calculator gave me -56.9 degrees. I will accept this angle and I will draw it. And I won't think exactly if this is the angle or not. So first draw it. So -56.9 will be an angle somewhere in here, a little bit more than halfway the quadrant. So go counterclockwise, -56.9 degrees. Now, when you look at the coordinates of OQ, you see that x is negative, y is positive. That tells us that OQ must be in quadrant 1. So in order to draw OQ now, we have to go across in here. It's a tan ratio, that's why we go across, right? And this will be our vector OQ. Now, next we will have to find the angle that RP makes with x-axis. So again, we're going to go inverse tan. That would be our alpha 2. 25 over 1. That's an interesting number. Let's see what angle we get. That would be interesting. So I got 87.7. So alpha 2 is 87.7 degrees. Again, the calculator will give us whatever the calculator can give us. So the smallest acute angle, right? And the most immediate smallest acute angle. So 87 would look something like this. It's a positive angle. And as you can see in here, this would be the exact angle as well, because as you can see, RP is located in the first quadrant, right? So this would be the corresponding for RP. So now if we want to find the angle made between the pink diagonal and this green diagonal here, so we're gonna have to bring them closer to each other. So I'm gonna grab this. Okay, make the Cartesian plane overlap nicely. So we have a bunch of angles here that will help us find the angle made between the diagonals. So that's 87.7, all right? And what we know here is if this is negative 56, then this would be also, the measurement of it will be 56.9 as well. So 56.9, right? So that tells us that the angles alpha, or the angle alpha made between the two vectors, would be equal to this little vector here, the pink little vector here, which seems to be equal to whatever is left over from 90 degrees. So 90 minus 56.9, so that's 33.1, this tiny little angle here. And whatever is left out of 90 from 87.7, which is about 2.3 degrees. So that's one way of finding this angle, right? So we'll say that the angle alpha made between these two vectors will be 33.1 plus 2.3, and voila, we got the answer, 35.4 degrees. So alpha is 35.4 degrees, the angle made between the two diagonals. Alrighty then, I hope this made sense, and I hope you found the instructions useful. Practice on your own and practice with confidence, like you can do this. It's not as difficult as it seems once you put your mind to it and you think that, I have no choice, but I gotta finish it. And you will find the tools and refer to the examples done in class so that you can get clues and ideas of what to do when. All right then, thank you and bye for now.